Swayam Prabha. Digital India. Educated India.
Welcome back to lecture number 2 on the topic vapor compression cycle under the subject refrigeration and cold chain management. We have seen about the construction and the working of a Carnot cycle and reversed Carnot cycle. How the COP of a reversed Carnot cycle, how the COP of a reversed Carnot cycle has been evaluated. Similarly, we derive the efficiency of a Carnot heat engine. We have come across with the term source and sink, which are all thermal reservoir. Source is a thermal reservoir which supplies infinite amount of heat to your body. Similarly, sink is a thermal reservoir to which the heat can be rejected or which absorbs the heat from the body. And we have seen the units which are used for evaluating the performance of the refrigeration cycle, that is BTU per hour, which is British thermal unit. Then we have seen 1 ton of refrigeration in terms of kilowatt, 3.52 kilowatt, how we arrived at that value 3.52. When we calculate, we will get around 3.87 or 86 kilowatt. But for practical purposes, 3.52 kilowatt has been used for a long time. Then in terms of kilojoule per minute, kilocalories per minute, 1 kilocalorie is 4.18 kilojoule. Now let us see the construction and working principle of the refrigeration cycle. How does a refrigeration system work? So primarily there are 4 major components. One is compressor, condenser, expansion device, and evaporator. So as I explained before, the basis for the vapor compression refrigeration cycle is the reversed Carnot cycle. So here it's a 2-pressure system. The condenser is operating at high pressure and the evaporator is operating at low pressure. So 1 to 2, then 1 to 2 is the process which takes place in the compressor. 2 to 3, then the process which takes place in the condenser. 3 to 4 is in expansion device. We are using an expansion valve. And 4 to 1 is evaporation process in the evaporator. So first 1 to 2 is, in the subsequent slide I will explain the process with TS diagram as well as on a pressure enthalpy chart. So 1 to 2 is isentropic compression. Process 1 to 2 is isentropic compression. One to 2 is isentropic compression of refrigerant. Compression of refrigerant. If you see the next one, so this is isentropic compression 1 to 2. Process 2 to 3, if you see in the diagram, the refrigerant, after the refrigerant enters the compressor as a low pressure, low temperature at the inlet of the compressor. The compressor raises the pressure and temperature to condenser pressure. So at state point 2, the condition of refrigerant is high pressure, high temperature. High pressure, high temperature. This high pressure, high temperature refrigerant goes to the condenser, where phase change process happens. Condensation process takes place. Vapor refrigerant will be changed into liquid refrigerant. High pressure refrigerant vapor will become high pressure liquid refrigerant. Process 2 to 3 is isobaric heat rejection process. Isobaric heat rejection process.
So, there is nothing but condensation process. Condensation process. So, let me draw the diagram here, the TS diagram. The temperature on the y axis and the entropy on the x axis. So, this is process 1 to 2, then we have got 2 to 3, 3 to 4 and 4 to 1. So, this is what we are discussing, that is heat rejection process, QC. Okay. So, anyway, I will be explaining about the 3 to 4 and 4 to 1 process after completing this one. So, process 2 to 3 is isobaric heat rejection process, where the refrigerant enters after compression. It is, if you see this diagram, it is initially cooled up to the saturation state. So, if you want, we can have this point as 2 dash if it is required. Otherwise, there is no specific state point for this one, and the condensation starts from this point and it ends at, and it's end at state number 3. So, the process is from 2 to 3, 2 to 3. So, during the phase change, when the refrigerant vapor is getting converted into liquid, at that time it is isothermal. Otherwise, 2 to 3 is isobaric heat rejection process. Then the next one is process 3 to 4, that is throttling process. It is a process in which the enthalpy of the refrigerant before and after process remains the same, that is enthalpy remains constant. So, the high pressure liquid refrigerant before it is enters the evaporator at state point 4. So, it is throttled. Normally, for an throttling process, an expansion device, that is an expansion valve, can be used, a capillary tube can be used. So, we will be discussing about the various types of expansion devices in the subsequent lectures. So, during throttling, enthalpy remains constant, that is enthalpy is equal to H is equal to constant. H is the specific enthalpy, that is in kilojoule per kg, it remains constant. So, on a TS diagram, this line will be an inclined one. On a pH chart, it will be perpendicular to the x axis. Then process 4 to 1. So, it is a isobaric process again, isobaric heat addition process, that is nothing but evaporation, evaporation. So, this is the evaporation process which takes place in the evaporator. So, what happens when the low pressure liquid refrigerant enters the evaporator? So, it takes the heat from the space where cooling is required and it gets converted into vapor. So, here at state point 1, the condition of refrigerant is saturated vapor, Similarly, at state point 3, the condition of refrigerant is saturated liquid. So, again in isobaric heat addition process, during phase change, when the phase change occurs and when it gets completed, the process is isothermal. So, 1 to 2 is compression, which takes place in the compressor. 2 to 3 is condensation, heat is rejected to the sink. 3 to 4 is expansion process, expansion or throttling process, and 4 to 1 is evaporation process or constant temperature heat addition process, which takes place in the evaporator. So, if you see the diagram, 1 to 2 is isentropic compression. Work is done on the compressor, that means it requires electrical energy
in order to compress the refrigerant from low pressure to high pressure. Of course, the temperature of the refrigerant also rises. So, the compressor is raising the pressure of the refrigerant from evaporator pressure, which is the low pressure, to the condenser pressure, which is high pressure. Then slight cooling is provided. Slight cooling is this one, because directly the heat rejection process does not take place at state 2. So, it takes at this point, and this is the vapor dome. The curve which is on the left side of the curve is called saturated liquid line, and this is saturated vapor line. The region that is between the saturated liquid and saturated vapor line is the two-phase region, which is a combination of liquid and vapor, mixture of liquid and vapor. So, now this is 2 to 3, then this is the isothermal heat rejection process, then 3 to 4 is throttling, and 4 to 1 is isothermal heat addition process. So, during this process, the heat is taken away by the refrigerant from the medium, and this heat is thrown outside. That is, heat is transferred from a low temperature region to a high temperature region, which is possible only with the help of external work. That external work is the electrical energy which is supplied to the compressor, Now, if you see the diagram, this diagram, on the right hand side, I am increasing the pressure of the refrigerant from low pressure to high pressure, that is from evaporator pressure to condenser pressure. Whereas on the left side, again the pressure of the refrigerant is reduced. From condenser pressure to evaporator pressure. For doing the process 3 to 4, I am not spending any electrical energy, not using any electrical energy. Whereas to achieve the process 1 to 2, as all of us know, compressor is not a power producing device, it's a power absorbing device. The amount of energy or power required to drive a compressor is huge compared to the energy that is required in case of a vapor absorption system which does not have a compressor. So, here electricity is used, but when I reduce the pressure, I am not using any electrical energy. So, why this has to happen? On one side I am increasing the pressure, on the other side I am decreasing the pressure. If I don't use electrical energy, that means my compressor will not function. So, I cannot compress the refrigerant from low temperature to. So, without the possible of external work or external energy, which is in the form of electrical energy in this case, we cannot transfer the heat from a low temperature region to a high temperature. If I don't raise the pressure of the refrigerant from evaporator pressure to condenser pressure, then condensation will not take place. Because here heat is rejected during condensation process. That heat is removed by the sink, which could be either air or water. In case of small capacity systems, air is used as the cooling medium in the condenser. In case of medium and large capacity systems, water is used. And though we can use water as a cooling medium to cool the condenser, it is not recommended for small capacity systems, because if you compare the water cooled system and the air cooled system, the initial cost is more, and not all places will have water scarcity may be more. But in case of air cooled condenser, air is available everywhere. Of course, the performance of the air cooled condenser system is less than that of water cooled system, but still for small capacity systems, the condenser is air cooled. So, this in order to achieve condensation, so I am raising the pressure and temperature of the refrigerant. If that is not done, then condensation will not take place. Then the heat of condensation cannot be rejected to the So if I am operating a condenser at 30 degree, and if the surrounding air temperature is 30 or 25, this process will not take place. I am raising the pressure of the refrigerant in such a manner that the condenser temperature is, let us take if it is at 40, the ambient at least a delta T of 10 degree centigrade. 10 degree centigrade. And if the cooling medium temperature is less, if air temperature is less, especially during winter, 20 degree or 25 degree centigrade, then the performance of the system is very good. So condensation, that is the reason, because of that's why we are using the compressor and also raising the pressure of the refrigerant. Now, the condition of the refrigerant at state 3, condition of refrigerant at state 3 is high pressure liquid, high pressure liquid. If I don't use an expansion valve, if I don't reduce the pressure, what will happen? In the evaporation, the liquid refrigerant will not be able to remove the heat from the medium or from the body substance, from the substance. So we have to reduce the pressure of the liquid refrigerant, and hence expansion device, and in the one which I have represented, an expansion valve is used. There are different types of expansion devices. Capillary tube also can be used. This is a very cheapest one compared to the other devices. We will be studying about the construction and the working of the major components in the second module in detail. So, right side the pressure is increased, otherwise the condensation will not happen. On left side, if we don't reduce the pressure, then it would be problem of evaporation. So, when the pressure is reduced, when the liquid refrigerant is entering the evaporator, it takes it requires latent heat for the evaporation. So, it is provided by the substance which has to be cooled, So, again here also temperature difference is required, otherwise this process will not take. So, 3 to 4 is throttling process which takes place in the expansion device, expansion valve, and 4 to 1 is isothermal expansion. So, the low pressure liquid refrigerant which is at state 4 takes the heat from the medium or the substance, from the body, and thereby that product is, the substance is cooled and the liquid refrigerant is evaporated, and it leaves at state 1 as low pressure refrigerant vapor. Low pressure refrigerant vapor. Again, this low pressure refrigerant vapor is compressed, where its pressure and temperature is raised to condenser pressure. Then again it goes through to the condenser, where it is condensed. The liquid high pressure refrigerant comes out of the condenser. Then throttling process takes place during process 3 to 4 in the expansion device, before the liquid refrigerant is evaporated in the evaporator. If you see the diagram, isentropic compression, then 2 to 3, from here the condensation starts, 2 to 3, then 3 to 4 is throttling process, and 4 to 1 is isothermal evaporation process, heat addition process. So, there are two heat transfer quantities. One is QE, that is the amount of heat absorbed by the refrigerant from the substance, and QC, amount of heat rejected during the condensation process, QC. And there is one work transfer quantity, that is how much electric energy has been used by the compressor in order to raise the pressure of the refrigerant from low pressure to high pressure. So, if you see the energy balance, QE plus WCO will be equal to QC, Since compressor and condenser starts with the letter C, so I have used C for condenser and CO for compressor. Let me repeat, CO refers to compressor and C refers to condenser. So, this is the pressure enthalpy diagram This is the pressure enthalpy diagram of a ideal vapor compression cycle. When I say ideal vapor compression cycle, it's a cycle in which there are no losses, no friction, no irreversibilities, etc. So to explain the process here, 1 to 2 is isentropic compression. During compression, the pressure temperature increases, the enthalpy increases. Then 2 to 3 is isothermal process. So during when the temperature is constant, during the pressure is also constant. So 2 to 3 is heat rejection process. Then 3 to 4, since the enthalpy remains constant during the throttling process, 3 to 4 is a line perpendicular to x-axis on a pressure enthalpy chart. 3 to 4 is a line which is perpendicular to x-axis on a pressure enthalpy chart. So here I am defining the refrigerating effect. That is in other terms, it is called the cooling capacity or refrigeration load. How much quantity of heat has been removed. Okay, so that is delta H, change in enthalpy, H1 minus H4, because 4 to 1 is evaporation process. And work of compression is, that is process 1 to 2. MR, actually it is M dot. All these are M dot. Mass flow rate of refrigerant. M is mass, M dot is mass flow rate. So let me use this one, M dot. So COP is the ratio of refrigerating effect to the work done by the compressor. Refrigerating effect is QE, work done by the compressor is WCO, and this is the compression process, WCO. So mass flow rate of refrigerant circulated into enthalpy H2 minus H1, and for QE it is H1 minus H4 enthalpy, H1 minus H4 enthalpy. So when you divide, the mass flow rate of the refrigerant term will get cancelled. The COP of an ideal vapor compression cycle is H1 minus H4 divided by H2 minus H4 divided by H2 minus H1. We have seen the components of, what are the components of a vapor compression refrigeration cycle, that is compressor, condenser, expansion device and evaporator. How to plot the various processes on a temperature entropy diagram and the pressure enthalpy diagram. How to evaluate the cooling capacity or refrigerating effect. How to evaluate the coefficient of performance of the ideal vapor compression cycle. If you see the COP formula, it is H1 minus H4, which is the refrigerating effect, divided by H2 minus H1. So in the subsequent classes, we will be seeing the performance improvement of vapor compression cycle, the pH diagram, the temperature entropy diagram, and also we will be solving numerical. With this, I conclude this lecture. Thank you.